Okay, so welcome to this tutorial. So when we got invited to do this tutorial some time ago, we foolishly accepted, and then we had to write it. And of course, in pitching the level of a tutorial like this, it's impossible to please the whole audience, because I can see people here who've been doing TTS for longer than me, and I can see people that maybe have never worked on it before. We've erred on the side of more basic material. And that's been a very carefully considered decision based on the sort of questions that I get asked a lot in teaching, and the questions we see over the years on the festival, HTS, and now sort of Merlin mailing lists and discussion boards. Those questions are almost always of the apparently naive form. I've made the demo work, how do I do Chinese? I've made the demo work, how do I change X? They're almost never about the neural network or anything like that. And they sort of tell me that a lot of people that are trying to play with DNN synthesis and other forms of synthesis have just got huge gaps in their knowledge. And part of the fault of that is that the demos are so easy to run. They come with prepared data and labels and all of that stuff. And people just think they have to change one line in a script and you've changed the language, something like that. So you're going to find quite a lot of the tutorials about that stuff, about dealing with the data, getting the data ready. And I'll explain the structure of the tutorial to you in a minute. So hopefully you've got that URL. That's my teaching website. There's a whole load of other stuff on there as well, but for now, just get those slides if you want them. It's the best value tutorial of all, so you've chosen well because you've got the most number of presenters, and we're going to do lots of quick changes between us. So I'd like to just welcome you. I'm Simon King, and I worked on speech synthesis for ages, and I'm the director of a centre in Edinburgh that's released things like Festival, that you probably have heard of, and more recently Merlin, as well as lots of other tools. My presenters will be in front of you in a moment. We've got Oliver Watts. He's going to talk mostly about a way of doing front-end text processing with minimal data and knowledge. We've got Srikanth, who's going to tell you the nitty-gritty of how you get your linguistic labels in the right shape for doing neural net speech synthesis. We've got Felipe, signal processing guru, who will answer everything you want to know about vocoding, parameterizing speech and reconstructing waveforms. And delighted to say we have Zhizheng Wu, the original author of the first version of Merlin, who's now with Apple, and he's going to talk about the core part, which is using the neural network. It's actually going to be remarkably short because of all the stuff that goes before it. And at the end, he's going to tell us about things that you can go beyond speech synthesis to do with Merlin. So we divided it up in the following way. I'm going to actually give you a very rapid tutorial on how text-to-speech works, restricting myself to how it's done with neural networks. And the reason to do that is because there'll be lots of people in the audience have gaps at some part of this process in the pipeline. And I'm going to describe it as doing synthesis with a ready-made system that we already have. I'm not going to tell you how to make that system, but we'll see the whole thing from end to end, from text input to waveform output. I'll then hand over to the team and we'll rewind and we'll see how you actually build that system. So we'll go through the pipeline again, but this time how you make the system. So that's what you'd be doing if you download it and try and make your own voice. And we'll break that down into various parts, front end, including another software tool called Ossian that Oliver will tell you about, as well as our tool, Merlin, and we'll just be using a standard open source vocoder world for the purposes of examples. And then in the final part, we'll talk about extensions that are already easily done with Merlin. Some there are already examples in GitHub, and others that will be fairly easily or less easily achievable by using Merlin. And Zhizheng will do those at the very end. We'll take questions, but in order to pack lots of material in and keep on time, we're just going to tell you when there's an opportunity for questions, rather than just firing questions in the middles of chunks of presentation. And when you see that slide, you can ask questions. Okay? The slides online, we've not put references on slides because it makes them very cluttered and it's impossible to be complete. Instead, there's a reading list at the end of the slides. So when we say something and mention a publication, it will be in that list at the end and there won't be a citation on the slides. We'll be linking everything to Merlin in practice, so the hands-on. We're not expecting you to do hands-on. Don't do that because you won't be able to pay attention to the presentation and the room will get very hot and noisy with all those fans. And we'll just show you some little clips of videos of the scripts being run, highlights of simplified versions of the scripts, and so on, just to show you where what we're saying in theory goes into the practical part of Merlin. And the videos will just look like this. They'll just be run-throughs of things happening, scripts running. So, for example, if you wanted to go and download Merlin, you'd go to GitHub, you'd surf around, you'd download it, clone it, get it ready to go, and you'd find there's an examples directory full of things, including a text-to-speech example and a voice conversion example. You'd find all of those things in there. Okay? So we're going to skip out of a lot of these videos, and we'll put those full versions online for you at the end. They're just a video of running the example shell scripts. They're what you'll see when you do it yourself. So the structure's like this. I'll give you my little tutorial. We'll hand over, and before the break, we'll get through essentially preparing the features. Not actually using any neural networks yet. We'll have a break, and then after the break, we'll come back and we'll use the neural net to do some regression, and finally generate a waveform, and then finish off with those extensions. So let's just make sure we all have some common background and do a very, very quick, very quick 20-minute tutorial on how text-to-speech works, restricting myself to the DNN framework, but many of you might have some background in unit selection, so we'll make the connection to that. There's a kind of classic pipeline that is used in unit selection systems, and this is carried over into almost all systems except ones that work from raw text. And that's we use something called a front end first to extract features from text, and then we generate a waveform based on those features. In unit selection, that's just a search problem constrained by some cost functions. So we're really trying to solve this end-to-end problem of text-to-speech. Now, there are people now trying to do this end-to-end thing, from raw text to actual waveform. We're not going to get to that point in this tutorial. That's not where we are. We're talking about a more conventional framework. So we're going to shrink that problem back to a slightly smaller problem, one that is more obviously addressable with machine learning. And we can cast that in sort of classical machine learning frame that will extract features from our raw signals, so extract features from text, extract features from speech. So we've got features, and then we'll do regression. A regression is just a prediction problem. Regress from one set of features to the other, from input to output. And that's how things are done in classical statistical parametric speech synthesis, whether it was with hidden Markov models and decision trees or with neural networks. And we'll see a lot of things that have carried over from the hidden Markov model framework. And we'll try and highlight those for you as we go along. And that will explain why some things are done the way they are. And therefore, we'll try and say to you where those things could be changed. So there are a lot of things that are just done that way because they were always done that way, and they need to be rethought. And we'll try and highlight that for you as we go through. So there'll always be this front end, and we'll talk about classical front end in my part, and a more machine learning idea of the front end in Oliver's part. We'll then put some statistical model in the middle of that and generate a waveform from the output of that. And so this core problem of statistical modeling is really just one of regression. And to do the regression, we're going to do feature extraction from text. We're going to do feature extraction from speech waveforms. And then we're going to do regression between those two things. So that's the core problem. So I'm describing speech synthesis then as a problem of regression. There's predicting a continuous value or a vector continuous value. And in fact, it's a sequence of things. So there's a sequence of things on the input, linguistic things. And there's a sequence of things on the output, acoustic things. And it's a sequence-to-sequence regression problem. And there's lots of problems to do with that we're going to have to solve, not least of which they're of different lengths. So we have to make some correspondence between these two sequences. And within the vast majority of this tutorial, we're going to do that while we prepare the features for regression. And the regression will be between aligned pairs of inputs and outputs. And we'll just touch on how you might do it from different length sequences towards the end. So what I've done then, I've cast this problem as one of sequence-to-sequence regression. And that's a deliberately generic description of speech synthesis, because I think if you can have that in your mind, then you can compartmentalize the problem into one of preparing input features, ready to do this regression, things that would be good as input to the regression, preparing output features, things that are predictable from the input from which we can construct a speech signal. And the regression module itself then essentially can be treated as a black box with vectors in and vectors out, and then you can imagine all sorts of things going in that black box. If you were doing so-called HMM synthesis, you'd be putting a regression tree in that box. We're now going to put a neural network in that box. So thinking this way makes a direct mapping between these techniques. So we're trying to do this problem, text to waveform. I'm saying that it's a regression problem. I'm going to say that regression problem's too hard. You could attempt it, but it has lots and lots of difficulties to it, which we'll pick up on as we go through the tutorial. So what we're going to do is we're going to rewrite that regression problem as not text, but linguistic features extracted from text using a sophisticated, complicated, traditional front end. And in fact, that's not something we can easily put into a standard regression model because it's symbols, not numbers. So we're going to have to turn it into numbers, a sequence of vectors. And the waveform, we're not going to predict directly to the waveform here. We're going to do the traditional thing of a vocoder. So we have to replace that waveform with a sequence of vectors as well. So we've got vectors going to vectors, two sequences, I'm going to put some sort of regression function between them, and that regression function is going to be a neural network in our case. Now we're going to draw various pictures of neural networks, and they're never going to be to scale because the real neural networks have thousands and thousands of units, so these are abstract. There aren't 3 inputs and 2 outputs, there's hundreds of inputs and hundreds of outputs. Okay, so I've talked about this very generic way to talk about text-to-speech, and that will hopefully give you a mental model in which you can plug the various parts of this tutorial. Where do they belong? Are they preparing the input features? Are they preparing the output features? Or are they some choices, some options you have for the regression? And it should be then become very easy to imagine extensions beyond what we're talking about today. Things that you could do better in the regression, features that will be better from text, features from the speech that will be better. So I'm going to now fly through the pipeline from text to speech, so you see all the parts, as if we'd already built the system, and then hand over to do that rewind of how to actually build that system. And that'll be slower, and it'll be step by step. So I've already introduced some terminology, so I'll be a little bit more careful about defining some of those terms as we're going through. I've said there's a thing called a front end. Front end, in the traditional sense, is something like the Festival speech synthesis system. The vast majority of what Festival does is front-end text processing. At the very end, it makes a waveform. Most of the code is to do with normalization and tokenization and part-of-speech tagging and all of that stuff. So there's a traditional thing called a front end that takes in text in its raw, unnormalized form, does all sorts of things to it, and produces what I'm calling a linguistic specification, which is things like pronunciation and structure. In the middle, we have some sort of regression that takes that linguistic specification, and we'll see we'll need to do some engineering to it to get it in a suitable form, and produces acoustic features from which we can generate a waveform with our waveform generator. Let's unpack the linguistic specification just a little bit. And at all times throughout the tutorial, always think, what we're telling you is just one way you can do it. We're not telling you every way it could be done, and we're not saying it's the best way, it's the standard way. So you can be imaginative and think of better ways or alternative ways. So linguistic specification is this whole thing and more. So this has got things like the original words. They've maybe been syllabified, if we're able to do that. We've got pronunciations. We've got the structure of those phonemes going into syllables. Don't worry about the slightly unusual syllabification. That's just the way Festival does it. And there's features such as stress on those syllables. There are individual linguistic features within that specification, such as phones or stress status of syllables. Those are the things we want to put into the regression. We want to find all of the features we can in that specification, write them out, and then use those as the predictors in our regression problem. And our acoustic features, I'll just leave a little bit vague at the moment and say they're a sequence of vectors at a fixed frame rate of maybe 200 frames per second, some representation of speech. So let's fly through the pipeline. And the first part of the pipeline that we saw before then is the thing called the front end. And the front end takes text and it makes this thing, it makes this linguistic specification. And so I want you to think of that as a form of feature extraction. And as soon as you think about feature extraction, you can think about lots of other ways of extracting features from text. You could do raw text features like, is it a capital or lowercase? Oliver will tell you about some smarter things you can do to get text features without a traditional front end. But we can put anything we like in the front end, and it can produce any sort of specification we like, because as long as we can turn that into a form for regression, we can use it. And we'll see there's a very generic and general purpose way of turning any structure like that into a sequence of vectors. That's very straightforward, and so you can be creative in the front end. You put more things in there, they could get used. For example, there's got part of speech there. We could add other things as well. We could have semantic taggers, chunkers, parsers, anything we liked. It's all going to be easy to turn into features. So the front end then is a feature extractor, and a traditional front end is made of a lot of components. It's actually a pipeline architecture. It's a very simplistic architecture, but it's one that's easy to sort of maintain and to engineer, and it breaks the problem down into a sequence of subproblems. And we're going to look at some of these subproblems and look at some of the sorts of things you would need to do if you wanted to build a traditional front end for a new language. And you find there's a very substantial engineering effort in every one of these modules. So each of these things are either learned from data, or they're hand engineered by looking at data, by looking at examples and accounting for those examples. And so this answers the question on those mailing lists. Okay, it works for English. How about Vietnamese? What do I do now? Well, the traditional answer is you do this. And that would be an expensive thing to do, but it would work, and that would be the way you would do it if you had the resources still. So let's take a glance inside a few of those modules just to get a better handle on the sort of cost that might be involved in making such a system. So I've written tokenize in the first box there. Tokenize is just chopping the string of characters into smaller pieces ready for processing, for example, trying to find things that might be words. And there's another step in there called normalization as well. So tokenization's fine if you've got white space. It's non-trivial if there's no white space. Normalization first involves deciding if something is a word, which you can attempt to look up in a dictionary or just predict from rules, or if it's a non-standard word, you need to do something to turn into words. So there's lots of classical ways of doing that, and we've got the world expert sitting there in the audience who knows how to do this. We might, for example, categorize non-standard words into some categories. So 2011 is a number that's clearly a year. #100 is a money amount. And then once we've done this classification, which will be a supervised machine learning problem, we'll label some data like that, train a classifier, for example. We could try rules. Each of those categories is handed off to a specialist module that knows how to expand things of its type. And that could be just rule-based. So expanding years into their pronunciation, we should be able to write some sort of simple rules and some sort of simple grammar that does that. Some things we might just be able to pronounce as a word. So IKEA, just hand it off to your letter to sound rules if you're sure it's pronounced as a word. So that's all fine. Another standard module in a pipeline is to apply part-of-speech tagging, and the primary reason for that is to disambiguate words that have the same spelling but different pronunciations before you look them up in the dictionary. So you need to tag them. And a part-of-speech tagger is a very standard piece of natural language processing technology these days. It can be made with extremely high precision. So it's essentially a solved problem if you've got the data. It's not easy if you don't have the data. And Oliver will show you how to do that if you don't have hand-tagged data to train a traditional tagger. We can just replace those part-of-speech tags with something else. So part-of-speech tags are things like nouns and verbs and so on. Typically, the tag sets we use are designed for text and they're rather too fine-grained. And things like Festival have two parallel tag sets. They have a really coarse one, which is very crude, and then they have this fine-grained one, and they use both of them for different purposes. If you wanted the simplest possible part-of-speech tag set, it would be closed-class words and open-class words. That would be helpful already for example, some prosody problems. Once you've tagged your words and you've decided they are words, you then need to find pronunciations for them. For English, the first thing will be to go and see if you've got a dictionary pronunciation, because that's always going to be more accurate than using the spelling. For other languages, you can just use rules. Again, Oliver will show you that you might be able to just use letters in many languages, not English, but many other languages, but you can do things to do slightly better than just using letters. So we're going to do the traditional thing of mapping to phones. Writing dictionaries is incredibly expensive. Think 2 person years to write a reasonable dictionary to get it all consistent and correct. A dictionary for speech synthesis might or might not have syllabification marked, or you might do that by rule. It might have syllable stress marked and things like that. So it's a more expensive thing than a speech recognition dictionary. That's a hard thing to write. Not necessary in some languages, essential in English. So your linguistic specification then is all of those things and some more things that I won't go into, and we can think of it as a structured object that a linguist would like, trees, things like that, things with features attached to them. And so our front end has done this feature extraction. But that linguistic specification is not suitable for doing regression. We're going to have to do something else, and Srikanth will get into the details on this, and that's we need to massage it, to process it, to do various other things, to turn it into the sequence of vectors. And we're going to call that feature engineering. So extraction is your front end, engineering is your rewriting of that specification in some other form that you could put into a neural network. And the terminology we're going to use for that is the following. We're going to think of this rich structured thing, which contains lots of information. We're going to do something a little bit dumb to that. We're going to squash it. We're going to flatten it so it's just got one level. And that level in the traditional front end will be the phone level. And we'll squash everything and attach it to the phone level. So attach everything as features to phones. So what we'll get is from this rich structure to a sequence of context-dependent phones. That's phones with extra features. Think of them as superscripts. That's still a symbol. So that symbol needs to be encoded as a number. So we have to think about how to turn symbols into numbers in the most generic possible way. Again, Srikanth will show you how that's done. And this thing is still at a linguistic time scale. So the ticking clock, the thing that's ticking through this sequence, is the phone. And we want to expand that out to acoustic frame rate, 200 frames a second. Because in our simplest system, our regression is going to be frame to frame, one at a time. So we'll call that upsampling, to go from linguistic timescale to acoustic timescale. So the whole thing looks like that. and Srikanth will fill in the gaps for you. So we take this thing at linguistic timescale, and through various procedures, including prediction durations, we'll get up to acoustic timescale. So we're going to have to do something about duration here. So linguistic objects don't have durations attached to them, but acoustic things have duration because they're instantiated. And then we're ready to do regression. So that thing on the right is the input to our regression model. So regression is going to be some statistical model. And if we think of it in its most generic terms, that's going to turn out to be really easy. It could be something as simple as this feed-forward neural network. Again, with hundreds of inputs and hundreds of outputs. And we put a vector in, we get a vector out. And I'm going to guess that in this audience there might be some people who, for neural networks, are still slightly mysterious. Probably the majority feel comfortable with them, but it's worth spending 60 seconds just to highlight the anatomy of a neural network to see what it's really doing. It's not some magic black box. We can just think of it as a sequence of nonlinear projections as follows. So there are some units, and there are connections like this that have weights on them. So when a signal goes down a connection with a weight, it's just multiplied by that weight. And those weights form themselves into weight matrices, like this. So from one layer to the next layer, it's just a matrix multiplication. That's just a linear projection. We form the units into layers, hidden layers. And those layers apply nonlinear operations. So it's a sequence of linear projections, nonlinear operations, linear projection, nonlinear operation. And think of that as a flow of information through the network from left to right. And on the input and on the output, we have some sort of representations of the problem. And the most important thing to know about a neural network is that inside those neurons, or more often now they're just called units, and if they're in a hidden layer, they're called hidden units. Hidden layer is just not an input or an output, it's in the middle. It does something nonlinear. It does a sum, which is linear, and it applies a nonlinear function. We're not going to get into the million choices of nonlinear functions here. There could be almost anything you want. There's a whole game of inventing nonlinear functions that you can put into neural networks. And then we have an output, and that output is often called the activation. So the reason I have lots of layers is to be able to project from your input representation, which is going to be something linguistic, to your output representation, which is something acoustic. This is clearly a very hard regression problem. We couldn't do this with a linear projection, so a matrix multiply isn't going to do the job. And we're going to do it with a whole sequence, a cascade of nonlinear projections through some intermediate representations. So the input's a representation of linguistic structure. The next layer is something a bit closer to acoustics. The next layer is a bit closer to acoustics, and the final layer is the acoustics. So we'll go through this sequence of representations. We'll come back to that idea, and we might actually use those hidden activations for something, and Zhizheng will show you a way that you might use these hidden activations as an interesting representation of linguistic objects that's tailored to the prediction of acoustic information. So that's just a sequence of nonlinear projections. So it's easy to do synthesis. Prepare your inputs. We'll spend a lot of time on that in a minute. And you put an input through the neural network, and you get an output. And then you put your next input, and you get your next output, and so on. Okay? So we're just going to propagate these through the net. And for most of the tutorial, I want you to think about this frame-to-frame mapping. So isolated one frame in, one frame out. We'll come back to sequences of things towards the end. This is by far and away the easiest thing to understand. When you build your first system, this is the one you want to build because it's fastest to train before you get into any fancy models. Okay? And we get the whole sequence of things out. And all we've got to do now is generate a waveform from those. So the acoustic features I'm going to leave a little bit mysterious because Felipe is going to unpack them for us. He's going to talk about the features that a vocoder uses and the difference between that and the features we might want to model. And that's going to be inherited from hidden Markov model-based synthesis. And he's going to remind us that some of those things might be changed. We might want to do better. So the acoustic features are something from which we can make a waveform. So they might be something like the fundamental frequency and the spectral envelope, or a source and a filter. So let's just think of the source and filter for now. Okay, so the whole thing together then is you put your text into your front end. Your front end runs lots of modules. It looks like one line in a script, but it's running 100,000 lines of festival code and doing all sorts of things, throwing very expensive models at the data. And I say expensive in the sense they were expensive to build. They're cheap to run, but they're very expensive to build in terms of data and labor. That gives us linguistic specification, which is what we'd really like to deal with, but we don't know how to use that to do regression. We have to turn it into numbers. And then we do this flattening, encoding, upsampling thing. So we'll turn that into a sequence of vectors. We'll add some duration information, this upsampling part. and then we'll push that through our neural network, and we can think of it coming straight out of the neural network and straight into a waveform generator. So it goes there through the vocoder, and we generate our little bit of waveform. And so if we're doing frame-to-frame regression, at each step, we're going to generate a frame of speech, a fixed duration, little bit of speech. And to make a speech waveform, we're essentially just going to concatenate those. We're not going to concatenate them in the dumb way. We're going to overlap and add them so you don't hear the joins, but that's essentially what we're going to do. So it's important to remember that the signals you're going to listen to are lots of little pieces joined together. So there's still overlap and add signal processing happening even in this parametric method. So something like what happens in unit selection. So that's in a nutshell. Hopefully that wasn't boring for the people that knew it, and it's filled in the gaps or given us something to hold on to for those who are new to this. So what we're going to do now is we're going to talk about how to actually build a system. The first part of that will be, what if you don't have a traditional front end like Festival? So we're not going to tell you how to build Festival. That will be not a tutorial, but an entire summer school or a year's course. I'm going to tell you how to build something much easier and more data-driven. After that, we'll talk about how you have to do some feature engineering to those linguistic features and to the acoustic features to get ready for doing regression. And that's going to fill up the whole first half of the tutorial, all of that, because that's by far and away the most important part. If you don't prepare your features right, there's no point having the most sexy neural network in the world with the most complicated hidden units if your features are useless. So you've got to spend your time getting the features right, and then we're just going to throw a simple regression model at it. And when we come to that, we'll also talk about duration at that point, and finally we'll generate waveforms.